Welcome everyone to the spectral geometry and the clouds. Please let me remind you to mute yourself if you're not speaking. I see a couple of mics open. Today we have the pleasure of having one of our co-organizers, one of our own, Jean Lagacé from King's College London, and he will speak about variations on Weyl laws for the Steklov problem on surfaces. Jean, your turn to speak.
Thanks a lot, Alexandre, for the introduction. So what I'm going to talk about today is something that has been researched probably for the last 40 years, 45 years. There's been a lot of developments, very precise Weyl laws for the Steklov problem on surfaces, way more than what you can say way more in that situation than what you can say for the Laplacian on surfaces, or for the Steklov problem, or the Laplacian on higher dimensional manifolds. And so I will speak with about 3 different results that are based on the same basic idea, but develop in different ways. Part of it with Simon Saint-Amand, who was a master's student in Montreal at the time, but is now a PhD student in Cambridge. Broderick Cosley, who's finishing his thesis at McGill, and a recent paper with Michal Karpukin and Josef Polterovich that should be on the archive either tomorrow or Wednesday. So let me first talk about the setting. So we'll start with some surface with boundary. It has finite genus, finite number of boundary components. And I look at what we call the Steklov problem here, which is looking at harmonic functions inside the domain omega. And I want to look at functions which are proportional to their normal derivative on the boundary. So the spectral parameter of this problem is a bit particular because it's on the boundary rather than being inside. But by now in this seminar, you should be used to this problem. We spoke about it last week, for instance. And there will be variations on the exact nature of this problem that we're looking at throughout the talk. And variations both in terms of adding a potential to the interior part and by playing with the regularity that the boundary has. So in all the situations that I'll be looking at, this is not true in general. You can have very wild boundary that would not allow for this. You have discrete spectrum. You start with eigenvalue 0, which is associated to a constant eigenfunction, and then the spectrum is discrete, increases, accumulates only at infinity, all the standard business. And since we will be interested in Weyl laws in spectral asymptotics, the counting function will often be a relevant object where we will look at the number of those eigenvalues which are below level sigma. Also, this is very beautiful right now. Okay. So the question is, what is the asymptotic behavior of sigma k as k goes to infinity? And these are what are called Weyl's law, Weyl laws. And in this context, we will want, these are what we aim for, either that the counting function will look like the perimeter of omega divided by pi times sigma plus some remainder that will depend on omega. And hopefully we can either make this remainder precise and have some further terms in the asymptotics that could inform us on the geometry of omega, just like in this first term we have the perimeter, or we can just make it as small as possible and have an idea on how precise that first term there here. Sometimes it's more convenient to give asymptotics in terms of the eigenvalues directly, where these 2 formulations here are equivalent. And again, we would want this R small to be either as small as possible or have further asymptotics for it that could inform us on the geometry of omega. So the outline today, we will speak about Weyl laws for, first of all, pseudo-differential operators on a circle, following results from the late 70s by Grigory Rosenblum. We'll talk about the Steklov problem in the case where we have smooth boundary, where in that same paper where the first part is done, it wasn't for when the surface is simply connected, but was also a bit less than 10 years ago investigated by Alexandre Giroir, Leonid Panofsky, Yosif Polterovich, and David Scher in the case of any surfaces. And the ideas that are present in these two papers, the one from these four people like 8 years ago, and the Rosenblum paper, will be present in the last three parts as well, where we will investigate a Steklov problem with a potential, with CR boundary, and with Lipschitz, and slightly worse even boundary. Well, slightly worse for some definition of slightly. All right. Before I go on, are there any questions about the setting, or I can? What is a pseudo-differential operator? First of all, well, I suppose that most of you will know what they are, but if not, the first part that you need is some symbol here, which will be a function of Rd times Rd to C. I consider, in our case, because these will be pseudo-differential operators on the boundary, it will be, you will see this as R1 times R1, where I consider the first variable to be some sort of spatial variable and the second variable to be some sort of momentum variable. And I can define an operator acting on functions in this way here as taking this Fourier transformed and inverse Fourier transform with kernel, using this symbol as an integral kernel here. And if I want to define these on a circle, well, I can just say that I act on periodic functions u, and that the symbol is assumed to be periodic in the x variable. One of the main examples of pseudo-differential operators that we know is actually a differential operator. Every differential operator are pseudo-differential, and it's a Laplacian, which has as its symbol absolute value of c squared. And the important thing to notice here is that it depends only on the momentum variable, and the birth of and the use of these pseudo-differential operator is actually born from the fact that differential operators with constant coefficients are diagonalized, so transformed into multiplication operators in a way by the Fourier transform, and there will be a special role for those operators whose symbol depends only on the variable xi. In the case of operators on one-dimensional objects, these are very well understood, and we get very precise behavior for the spectrum of those operators. So the first example that we can look at is the Laplacian on the circle. So the Laplacian on the circle, we know exactly what its eigenfunctions are. So eigenfunctions are e to the I kx k in z, and the eigenvalues are k squared z. And the one thing that I want you to notice is that, as we said earlier, its symbol as a psi dio is norm of c squared, which I will say call a of c. So lambda k is this, and so lambda k is a of k. And here I have purposefully not necessarily ordered them in increasing order. If you want to label them in increasing order, take your favorite mapping from z to n, so that these will increase. And this is not really a problem, but this identity here is what is quite important in this situation. And the second example, which will behave in exactly the same way, is the Dirichlet to Neumann operator on the disk. So what the Dirichlet to Neumann operator does is it takes u in a smooth function on the circle, it sends it to the harmonic extension of u, and then back to the normal derivative of this harmonic extension on the boundary. And the eigenvalues of this operator here are the Steklov eigenvalues. So this is a particularly relevant operator to our situation here. And in this case, the eigenfunctions in the interior are r to the n e to the I n theta. On the boundary, it's still just e to the I n theta, and the eigenvalues are therefore 0, 1, 1, 2, 2, this, which is equal to absolute value of n in z, which is not really a surprise because the symbol is exactly a of xc is equal to absolute value of xc. So again, we see this relationship between an operator where the symbol depends only on the on this momentum variable xc and the eigenvalues of this operator on the circle. And this was formalized by Rosenblum, where he has two theorems about elliptic pseudo-differential operators on the circle. Well, I mean, there's more than two, but two that I'm going to talk about right now. So the first one is that suppose A is an elliptic pseudo-differential operator on S1, and that A is the operator associated with a function that depends only on C, then the spectrum of this operator here is equal to the evaluation of this symbol at K plus an error that depends on K, that's precise in K up to infinite order for K in Z. So basically this behavior that we saw for the two previous examples is actually what we expect, except that maybe we have a very small error at the end. And the second part is that if A also depends on X, there exists U unitary such that U star A U is equal to B, up to smoothing operators, and B is an operator with symbol B. B depends only on this momentum variable. And this is really a result about operators on the circle, where you will be able to transform the principal symbol, the main part of the symbol, into a symbol depending only on xi, using a canonical transformation associated with the arc length parametrization, or a weighted arc length parametrization. And the rest of the procedure is done.
Sorry, Jean.
Yes.
The operator should be self-adjoint.
Oh, yes, of course. You are completely right here. You need a self-adjoint operator. And the rest of the procedure is based on a recursive algorithm to use the principal part that we have transformed into an operator depending only on the momentum variable, in order to cancel out the rest of the dependence on x. So what do these theorems tell us? I mean, they're a bit technical, but what they tell us at the end of the day is that if my symbol depends only on xi, then I know the spectral asymptotics really well. And if then the symbol, I have an operator whose symbol depends on x and xi, I have an explicit procedure that I can use to transform this this operator into another operator with the same spectrum and symbol that depends only on xi, and so I can read up from that new operator the spectrum, the spectral asymptotics, and then it just becomes a matter of actually performing those computations in an explicit manner. So the goal then is, can we from those explicit computations extract any sort of geometric information, for instance, from the surface on which we started. So, and let me just mention that one of the main ideas in this proof here is that perturbations by pseudo-differential operators of a small order do not affect the spectrum much. So if A is elliptic self-adjoint and Q is self-adjoint and Q sends some subelative space H minus S to L2, elliptic self-adjoint, and here even maybe positive order. Then lambda k of A plus Q minus lambda k of A is big O of k to the minus S. And so we use the exact representations that we have for operators whose symbol depend purely on xi to get this in the first place. And then in the recursion algorithm, as we get further and further down in the spectrum, we are all able to get the kind of precision that we want. So this is, and we use the fact that pseudo-differential operators of order minus S have this mapping property here. So this is one of the ideas here that will be exploited again in the future. So let's now see how this can be used in order to get a Weyl law for the Steklov problem on some surface with boundary. And we will start with the case of a simply connected surface. So we start with some domain omega here. And the Riemann mapping theorem tells us that I can send this via some phi here conformal to the disk here. And so here this omega has a smooth boundary. And the idea is that this sends the problem Laplacian of u is equal to 0 in omega, and normal derivative of u is sigma u on the boundary. This gets mapped by this phi to Laplacian of u is 0 in the disk, and the normal derivative of u is sigma absolute value of the derivative of the conformal factor times u on the circle here. And so I started with a pseudo-differential operator on a surface that I don't really know how to deal with, and then I can map it to a different spectral problem on the disk, where here I will call this beta as a positive weight, where beta depends on x. And so in this situation, the operator has symbol absolute value of c divided by beta of x. And through this unitary equivalence by some sort of weighted arc length parameterization. So this is equivalent to an operator with symbol c divided by integral on S1 of beta, which will be c divided by the perimeter of omega. And so the consequence here, is that sigma k of omega is equal to sigma k of the disk divided by the perimeter of omega plus an error of any precision that we would like. Now, what does that tell us? Well, first of all, this is a very precise spectral asymptotics. Usually when we're used to Weyl laws for the Laplacian on surfaces or manifolds, we don't get error estimates that are that precise. But the second thing that it tells us that if we are looking for spectral invariance, this is not very good. Because from polynomial spectral invariance, we will never be able to get more than the perimeter here, because everything is in this sub-polynomial or super polynomial error term. So, but it does tell us that the parameter is a spectral invariant. Now, what do we do if the surface is multiply connected? Well, if the surface is multiply connected, So say it looks like this. The idea is to cut, and this is the idea that's in the paper by Giroir, Barnowski, Polterovich, and Schur, is to cut along a small tubular neighborhood of each of those components, and then you send this via some phi conformal to something that will look like 3 disks, where you fill the rest of what's inside this annulus like this. And for these 3 disks, we know what are what is the Weyl law. We just computed it, and so spectrum of disjoint union of disks is the union of their spectra. All right, so the idea here is that we can use the computation that we have made in the case of the simply connected case in order to get the asymptotics for all of those, where we then get the Weyl law that sigma k of omega is equal to the spectrum of a union over the boundary components. So union over J of 1 over Lj D, where this is the length of the J boundary curve, plus big O of k to the minus infinity. And oops, sorry. Here, basically, there is an argument to be made, but it's basically by arguing that the symbol only depends on a neighborhood of what happens in the neighborhood of the boundary. It does not depend on the interior part. You can argue that the spectral asymptotics of this surface here, omega, that has no that is all attached, is the same as the spectrum of this union of 3 disks up to infinite order, and that's how you get this thing here. Now, in that paper, they also give us an algorithm to decouple the sequences. So basically, given that that sequence here, they give an algorithm where you extract from that sequence first a sequence that corresponds to the longest boundary length, then to the second longest, the third longest recursively, and so on and so forth, until you have extracted both all the number of boundary components, but also the length of each of those. So here the upshot is by decoupling that these sequences the number of boundary components plus their respective lengths are spectral invariants. And here, Steklov. Spectral invariance. The con, we can't say more. From polynomial spectral invariance. And in particular, we cannot have any information from the inside of the surface from these invariants. Yes. Okay.
I think Lenny had a question, perhaps. I was just unmuted. Okay, we'll just remute him.
Okay. All right, and so our goal now is to find a variation on this problem that would allow us to say something about what happens inside. And this will be the Steklov problem with potential, where the setting is that I start with omega, a surface with boundary, some potential tau.
Jean, sorry, it's Alex. I have a question.
Yeah. Yes.
So what do you mean by a polynomial invariant?
Basically, from either the Weyl law at a level of precision that's a polynomial level here, you don't go into exponential size errors, but also from things like Riesz means, because from Riesz means, if you have that level of precision on the eigenvalue itself, you will get a similar amount of precision on things like Riesz means of the eigenvalues as well. But you could get them, for example, for something that's closer to the notion of a zeta function of the spectrum could give you more information. I mean, I don't know if it does, but it could a priori.
Thank you.
And Zev?
Yeah. What is the Steklov spectrum of the union? Is it the sum of the eigenvalues?
It's the union of the spectrum.
The union of the spectrum. So you have essentially a finite number of arithmetic progressions.
Yeah.
Okay. Thank you.
Of slightly perturbed arithmetic progressions that you then
perturbed by this
very small, yeah. But this decoupling can actually work as soon as you have a perturbation that goes to zero as the parameter goes to infinity. It doesn't matter that it doesn't need to be that small.
Okay, thank you.
Which is actually important in the decoupling that will happen with the potential. Where in this situation, we add this potential inside. The reason why I remove lambda from the potential is that this will actually be the case, this discrete spectrum looking in this way and with this problem being completely well defined. This is, if we don't want to do anything a bit more complicated, this works for all lambda except maybe, well, not just maybe, except some discrete set.
Sorry,
Yes.
why isn't lambda is not negative?
Hmm? Lambda.
That's the problem. I think that lambda is non-negative.
Lambda can be whatever you like here.
Okay, thanks.
I mean, except for some discrete set that I don't want to get into.
Okay.
And here, the conformal equivalence. So I will again just draw it for something simply connected. But the same procedure that worked in the multiply connected case for the Steklov problem will still work here. So when I send this omega conformally to the disk like this, it will send the problem Laplacian u, well, Laplacian plus lambda tau u is 0 in omega, and the normal derivative of u is sigma u. On the boundary, this gets mapped by a phi to the problem, which is Laplacian plus lambda tau d phi squared u is 0, and this is in the disk, and normal derivative of u is sigma, the same beta as before, u on S1. And so again, I get this problem that we had before mapped to something slightly more complicated, but on the disk. And this is the operator that corresponds to this is some variation of the Dirichlet-Neumann map that will have a symbol depending only on a small neighborhood of the boundary. And in this case, the symbol of this operator will be a of x xi, which will be xi divided by beta, just like with the Dirichlet-Neumann map that we had before. This was the first term, minus lambda tau divided by 2 beta xi, minus and here tau and d squared, minus lambda over 4 beta xi squared times some function of tau and phi that I don't want to detail too much right now, plus lower order term. And when I go via the unitary equivalence that I discussed earlier, this is unitarily equivalent to a symbol B of xi, which is equal to xi over the perimeter of omega minus lambda perimeter of omega divided by 4p xi plus lambda perimeter of omega divided by some other function here, c squared, times some integral of tau phi prime squared divided by beta plus lower order term. So the point here is not to know, oh, and this is a minus here, is not to know precisely what these coefficients here for you. I don't want you to take this on. What I want you to look here is that, first of all, there is no term of order 0, and this is what will make the perturbation in the eigenvalues be small enough to decouple in the multiply connected case. And the fact that I have more terms, I will have some geometric information that I will be able to extract from this. And in the special case where tau equals 1, I have here that the eigenvalues of omega will be equal to, well, the symbol B of xi will be xi over L, this will be the length, minus lambda over 4 pi xi L. And what's important here is that this term here has the integral on the boundary of the geodesic curvature. And again, so plus lower order term. And we know that the eigenvalues are just evaluating that at the integers. And by evaluating that at the integers, it means that I will be able to get this integral of the geodesic curvature as a spectral invariant, which will mean at the end of the day that for tau 1 and lambda not equal to 0, we can extract the Euler characteristic of the surface plus its number of boundary components and therefore the genus if it is a domain in a space of constant curvature. And this will be done just using the Gauss-Bonnet theorem. So we need to know a priori that you're in a space of constant curvature, because otherwise you will get some linear combination of an integral of the curvature and the Euler characteristic. But so this tells us that by adding this potential, and maybe for other choices of potential, we can get different geometric invariants. We didn't investigate this. We can get more information from the spectral asymptotics, and also potentially that from computations of later, of further symbols in this recursion, we would be able to get more information. But as with all of these pseudo-differential computations of the symbol, the further down you want to go in the recursion algorithm to get the symbol, the more the computation becomes convoluted, and the harder it gets to just look at it and see out of it pop out some sort of geometric invariant. Now I will, for now, skip the CR boundary case. I want to talk about the Steklov problem with Lipschitz boundary. So here, what I want to do once again, and so if my boundary is Lipschitz, first of all, I don't have access a priori to pseudo-differential tools, because pseudo-differential operators assume some form of level of regularity on the boundary. In the CR case that I didn't really discuss, you can still use some of those tools up to some level in the recursion, but with a boundary that's only Lipschitz, I can't really hope to at least directly use the pseudo-differential tools. However, I still have this conformal map. So let's say I have this quite bad boundary, I mean, I guess that how I drew it is smooth, even if only oscillatory, but imagine that this is not smooth, it has corners and whatever you want it to have, omega. I can still send it to the disk here. And I would like, for this problem here, normal derivative of u is sigma u to be sent via phi to the problem Laplacian if u equals 0, and normal derivative of u is sigma beta u. So I would like for this to happen. Now, one of the problems is that, well, if my boundary is Lipschitz, okay, this is defined almost everywhere, so this could still make sense, but maybe my boundary is slightly worse than Lipschitz. The isospectrality that you computed there, when everything is smooth, you can just verify that all the differential equations still work in the same. So the strong form gives you exactly what you need, but it's not clear here that this phi leads to two isospectral problems. It's not even clear that this beta here, what exactly, we need to know properties of this beta in order to say anything. So if the boundary of omega is Lipschitz, beta is in LP of S1 for some p greater than 1. So there exists p greater than 1 with beta in some LP space. And this will be an observation that we will use. And so the eigenvalues here are defined via some variational principle where I would like sigma k of omega to be the minimum over some spaces ek, max over u in ek, except for 0 of this integral here over omega integral on the boundary of omega u squared dlg, where here ek is a k plus 1 dimensional subspace, and here this is the main problem that you have when the boundary is maybe not regular enough. Normally, when you work with smooth boundary, you just say, okay, of the subleved space W12. But here you have to be a bit more careful, and I will write this as W12 boundary of omega, which is essentially the closure of u in W12 such that the integral on the boundary of u squared is smaller than infinity, closed with the norm integral on omega of grad u squared dg plus the integral on the boundary of u squared dlg. Now, if the boundary is regular enough, and Lipschitz is good for that as well, this subleved space is equivalent to the usual one. So you don't have to worry too much, but we have to be a bit careful when we have less regularity. And if instead here, I want to look at sigma k on the disk with some weight beta, then here I have that. And here I have on the circle, I have this weight beta here. And because the Dirichlet energy is conformally invariant, and because this denominator is just the push forward measure by this conformal mapping, it's easy to hope a priori that these are just isospectral because you are looking at exactly the same formulations on both cases. The issue here is question, does phi induce a map of the Sobolev spaces? And in general, it might not be the case. And for the both problems to be isospectral, you need that phi, you need phi to do so. And did I lose one thing? I think okay. And so we introduced the notion for us that will be the right one in terms of regularity is what is the integrability class of this boundary conformal factor. So we say that that omega has boundary conformal regularity X if beta is in X of S1, where this here is just some function space. And we prove that if omega has, so we'll call this BCR, has BCR L log L, which here is a space that sits between L1 and LP for P greater than 1, then phi from the disk to omega induces phi star from W1 to D of omega to the same thing in the disk. And here, this is an isomorphism. And basically, this is what we needed for the variational characterization to be equivalent. And therefore, under this condition here, I have isospectrality of the two problems that I mentioned a few slides ago. But here, I mentioned that if the boundary is Lipschitz, then they are in LP for some P greater than 1. The boundary conformal factor is in some LP for P greater than 1. What this means is that for Lipschitz boundary, and actually something that's less regular than Lipschitz boundary, you can go up to this L log L regularity, which includes some cusps that are slow enough, for instance. You do have isospectrality between these two problems. And then, so now that we have isospectrality, we need to study this weighted problem on the disk, but we still have the same problem that this is not smooth. Beta is in some, it's not even differentiable once. So we can't use at that point the pseudo differential techniques. And the idea will be to look at the eigenvalues of the inverse. So the Dirichlet-Neumann map with L log L weight has compact resolvent. So we will look at eigenvalues of its inverse, which correspond to the quotient 1 over sigma k, which will be the min over codim f is k max u in f, except for 0, of integral of beta u squared on the boundary divided by this here on the disk. And this has been studied a lot by Riemann and Solomniak in the 80s, and then people later who made who extended their work. And they have two lemmas. The first one is if A and B are compact, positive, and the lim sup as lambda goes to 0 of lambda inverse times the number of j such that lambda j of A minus B. And here I want B to be smaller than A, is greater than lambda, is smaller than epsilon, then, so this I will call n of lambda A minus B, then n of lambda A minus n of lambda B is smaller times then n of lambda A over n of lambda B goes to 1 as lambda goes to 0. And their second lemma is that the number of eigenvalues with the Dirichlet to okay, if you don't mind, I will take just 2 minutes more. And the second part of the lemma, we can control the eigenvalue counting function via the LP norm of the weight. And in fact, the L log L norm of the weight. So here, P greater than 1. So in the end, take beta epsilon converging to beta in LP. And here, all of those guys are smooth, satisfy Weyl's law. And you know that at the end, beta also satisfies a Weyl law as well. So the number to the conclusion is that the number of the counting function for omega with omega Lipschitz will be pi over the perimeter of omega sigma plus small o of sigma, here we cannot really go any further down than that. So just to mention, without writing extensions there, first of all, you can do this not only for simply connected surfaces. Again, this works with a slightly different method as earlier for multiply connected. However, the higher dimensional case is not really achievable with these conformal mappings instead, so we need to develop completely new techniques if we want to work out the case of higher dimensions, and I will finish here.
Thank you very much, Jean, for the great talk. So we have time for a few questions.
I have a question. In the beginning, you were asking about pseudo-differential operators and the reduction to constant coefficient. Do you need to have classical symbols for that, or you can take only any elliptic operator?
You need to have a. It doesn't have to be classical in the sense that you don't need to have integer orders. You can, but you need to have a decreasing sequence of.
But you need to have some homogeneous.
Yeah.
Homogeneous. Okay.
Yeah. There is some homogeneity that was required.
It's in fact, it's a Birkhoff normal forms or something like that. For the
I guess in that, yeah.
Because it seems it's a very particular case of the Deux-Termes trace formula. Because then the periodic orbits are just the circle.
Yeah. In a way, it's a
very particular case of that.
Yeah. We're in a way we are able to go as far in the asymptotics for the eigenvalue directly.
Yeah.
From
depends only on the Birkhoff normal form of the periodic orbit. So it's what we say, but it's of course you can do it in a more direct way. But it's.
Can I say something? It's Alexandre here. I think in the case where there is multiplicity, the Stern-Riemann formula might not be sufficient. So if you have, say, a surface with many boundary components and they all have the same length, I believe that using the Stern-Riemann formula, you could not extract how many of them there are with the same length. Okay, so it's been a few years since we worked on this.
You have to check. I cannot answer directly, but
okay.
Okay, I don't want to. Okay, you can extract the length of the component, but that's just to mention this analogy with the Stern-Riemann formula, which is related to the Birkhoff normal form, which is related to the fact that you can reduce to some operator with constant coefficient.
Yeah, I mean,
some convolution operator.
You are correct that it's possible that I mean, I mentioned where I have seen the method and where I have learned the proof from, but it's true that
just some kind of background information.
Yes.
Thank you.
I have another question. Maybe I can ask another question concerning the small terms or the exponentially small term. Do you try to compute them using the kind of tunneling effect?
The exponentially small terms, I haven't tried to compute them directly. I think there might be something in the work of Galkowski and Toth when they looked at the fact that as soon as you get inside, the eigenfunctions are exponentially small, and there's this paper by Polterovich, I think it's with Toth and Suresh, where I think some of these issues might be.
There was some lecture in your seminar on that.
Yeah.
Some time ago, I remember now.
I was wondering, Jean, so you said you could extract the perimeter of the boundaries and also thanks to your potential, the Euler characteristic and things like that. Is there other things you can extract? Do you know that? Or?
I mean, what I've told you is all we were able to do.
Okay.
Now, I mean, I expect that we will be able to extract more if one does computes things later on in these asymptotics. It's just that yeah, we were not able to make sense of the coefficients that we got and see if they have some geometric interpretation.
But
There,
is the
but-
thing explicit enough so that if you wanted to extract something, you could try and engineer the problem so that you could.
It's quite explicit, yeah. It just gets very, very messy.
There's time for more questions. If not, I think we can thank the speaker again. And we do not meet next week because there is an extraordinary session of the gemstone. I mean, maybe Alexandre, you can talk about it.
I got a quick question, John.
Oh, yeah, sure.
So you say that you mentioned something about cups, right? And then you say it can be. Can you allow any order of cups on the case where it's
No, you need that it's slower than square root cusp.
Okay, so
but actually,
yeah.
From a square root cusp on, you get a continuous spectrum. So you absolutely cannot expect any sort of Weyl.
Okay, so it's 1/2. You think that's dimension dependent? Well, you did mention that your method doesn't generalize to higher dimension, but
this specific method, no. But this fact about having continuous spectrum, there's a paper by Nazarov and Taskinen.
Okay.
That looks at cusps.
Yeah. Okay. All right. Thanks.
All right. Cheers.
Have a good day.
You too. Thanks.